Alrighty, welcome back to videos talking about how to do free body diagrams. In case you missed it, we were talking about forces and unbalanced forces and how can we draw a diagram that really helps us figure out how unbalanced the forces actually are and how that's causing some motion in objects. As a quick recap, the video before also went over this, but in case you missed it, in order to draw free body diagrams, we start with a box that represents our object of focus. And from that, we are drawing arrows that represents different types of forces that are acting on that object. We have to be careful about the direction of the arrows as well as the size. So, yeah, we'll just get into it. Okay. So previously in the earlier video, I went over, I went over this one and I went over this one. So that leaves us with this one. Okay. Scenario number 3, a student rests a backpack on their shoulder. The pack is suspended motionless by one strap from the shoulder. So what forces are present on that backpack? Well, gravity is definitely pulling down on that backpack. We don't see any springs, so there's no spring force. Because the backpack is attached to a strap and the strap is hooked over that kiddo's shoulder, there is a tension force in that strap as it's attached to the backpack. I don't believe there is a normal force in this one. We are not moving, so there's no friction and no air resistance. So the only two forces that we have to deal with are gravity and tension. So I'm going to erase this one. And let's go into drawing a system schema. So the objects that we have a backpack. I'm just going to put BP for backpack. We have the shoulder. And of course, and always, we need to have the earth included in our system schema. Because we're focusing on the backpack, we're going to use a dotted line around it just to emphasize it. And let's go ahead and think about what are some forces that are relating everything. So if there's an earth, there's gravity. So gravity is what's pulling down on the backpack. So I'm going to label that here. Remember, it's a dotted line because it's a non-contact force, or it's an action at a distance force. We don't have to actually touch anything to experience gravity. I know I said that if you have gravity, you'll probably see the normal force, but in this case, because the backpack isn't sitting on something, there isn't really a normal force. Instead, gravity is being balanced out by the force between the backpack and the shoulder, meaning within that strap, right? So because they're contacting each other, it's a solid line, that is going to be the, what did we say? Tension force. So force of tension. Okay, and I think that's it. That's all that's really acting on that backpack. Gravity's pulling it down, shoulders helping to hold it up because of the tension in the strap. So, remember my hint to you, when you go from system schema to free body diagrams, it's like you just focus on this part here and you say, okay, my object of focus has what forces acting on it. So, we've got tension and gravity that we're going to be including in our free body diagram. Remember, free body diagrams start with a box that represents our backpack, and then we say, okay, we have tension and we have gravity, so which directions are they going to go in and how big are they going to be? Well, because gravity pulls down on the backpack, our arrow for gravity is going to go down. F sub grav is what we're going to label it. Then the tension force has to be equal to the force of gravity, but in an opposite direction. Why is that? Well, think about it. If gravity was larger than the tension force, that backpack would be falling to the floor. If tension was larger than gravity, the backpack would be springing upwards, and that's not happening. So tension force has to be equal, again, do the best that you can, but opposite to gravity. So it should look something like that. Okay, I'm going to go ahead and erase this one. Bloop. Sounds good. All right, let's go into the very last problem. This little video cracks me up. So a car is coasting to the right and slowing down. We are neglecting air resistance, which means we do not care about air resistance. Even though it's there, it's so small. It's such a small force that we're not going to worry about it. So, what forces are possibly present? Well, obviously there's gravity, because otherwise the cars would be floating like in Back to the Future. There's no springs, so there's no spring force. There's no cables, wires, leashes, ropes, whatever, so there's no tension force. Is there a normal force? Yes, because otherwise the car would be sinking all the way through the road. Is there friction? Absolutely, because that car is slowing down. Why is it slowing down? Because of friction. And because we said we're neglecting air resistance, we're going to cross this out. Even though it exists, it's so small that we're not going to actually worry about it. So, 3 forces that we have: gravity, normal, and friction. Let's go to our system schema and see what that's going to look like. Objects that we have the car. That's our object of focus here, so it's a dotted line around it. We have the road. We have the earth. And, wow, how did I spell that? Let me redo that. Hold on. Messy. Earth. That's better. Alright, so some forces between it. Like I said, always start with gravity and see who's connecting to what. So the earth and the earth and the car has the force of gravity between them, right? That's why the car is on the ground all the time. There is technically the force of gravity between the earth and the road. If you wanted to include it, you could, but we don't have to. Sometimes adding too much gravity lines makes system schema a little bit messy, so we're going to kind of forego that right now. But then we need to think about the other forces that we had. Remember, we had the normal force, or we ask ourselves, who is supporting the car so that the car doesn't just go straight into the center of the earth? Well, so the car and the road experience a normal force. The road is supporting the car as the car sits on it. Then we said that the car is slowing down because of the force of friction. Well, the car is in contact with the road. The road is kind of a rough surface. That's where the force of friction is coming from. So there's our system schema for the car, road, and earth. If I go to my free body diagram, think about, well, what am I going to be including in that free body diagram? It's going to be this chunk here. I have my car, which will be represented by a box, and then I need to think about directions and sizes of the friction force, normal force, and gravity. Sometimes it works, sometimes it doesn't. There we go. Okay, so my free body diagram for this scenario, the box is going to represent the car. All right. Now, as always, gravity and normal force are easy to talk about and draw because they're equal but opposite. So gravity is pulling down on the car. Normal force from the road is equal but opposite. So that way the car just stays nice and steady on top of the road. Then, it says that the car is coasting to the right and is slowing down. And we know that the slowing down part is because of friction. But which way am I going to be putting that friction arrow? Am I going to be putting it towards the right-hand side, or am I going to be putting it towards the left-hand side? Since the car is moving to the right, so motion is this way, friction acts in the opposite direction. So the force of friction has to be this way. All right, let me erase these little arrows over here. Motion is going this way. Let me label this. This is the force of friction. Okay, now, this is, again, a scenario where you just double check, does my free body diagram match what I see happening in the scenario? So, because there's no applied force from a gas pedal or a brake or anything like that, the car is just coasting. The only force that is really changing that object's motion is the force of friction. So looking at the free body diagram, that force of friction is causing the motion to slow down, which is what we're seeing in real life. Cool, so that is the free body diagram for that scenario, and that's the last one that we had to do as our intro to free body diagrams. If you need to rewatch these, go ahead and rewatch them. Otherwise, you are now prepared for the afternoon time. Email me if anything else comes up.